first lecture is by Professor Senthilkumaran from IIT Delhi. He is a very known figure in the field of singular optics, and then many of us who work in this field read their paper most of the time, and it's a great opportunity for all of us to hear directly from him about this field. So with this, I request Professor to give the lecture.
Thank you very much, Gautam. Yeah, we are starting 10 minutes late, so I will get, don't look at this watch, 10 minutes I will get extra, right? Okay, today the topic which I have selected is topological constructs and topological phases in polarization singularities. So the outline is given here. First, I will give a brief introduction to polarization of light, and before going into polarization singularities, I have to talk about phase structured light, which means phase singularities. And then some of the topological aspects such as many things, sign rules and conservation laws, all these things I will talk. And after talking about the phase singularity, the natural extension is go to the polarization singularity. That is a structured light. Polarization distribution has a structure. That is why it's a structured light. And in polarization singularity also, what are the topological aspects, sign rules, those index rules are there. Conservation, all these things are there. Then I will also talk about some of the new spheres called a model sphere. First I will talk. It is also called the Paget sphere, sometimes people say. Block sphere, directions in fact, and Poincare sphere, and in Panchratnam phases in all these spheres, how do we get it? And some of the newly introduced Poincare spheres called higher order Poincare spheres or hybrid order Poincare spheres I will introduce. These are the newly introduced spheres very recently, less than 5-6 years back. So to deal inhomogeneously polarized lights. Now coming to the polarization of light, yesterday I saw Nirmalya Ghosh talk. He has talked extensively on the Stokes parameters, S0, S1, S2, S3, because the Stokes parameter is very interesting because it always gives intensity. All are intensity measurements, as you can see. So intensities are very easy to detect, unlike phase. In Jones matrix, in Jones formalism of polarization, you have amplitude and phase. Here, we have only intensity differences. You can see that, which is the laser pointer. Yeah, okay. So you see the differences. The difference between X, if you decompose a light into XY component, or you can decompose the light into 45-degree oriented linear and minus 45-degree oriented linear, or RCP, LCP. You can decompose light in many ways by selecting appropriate orthogonal basis. So the differences in the intensity which you observe by decomposing light are appearing here as. So S1, S2, S3 are actually difference in the component intensities. And this gives, in fact, there is information about the phase also in that one can get only by extending this idea a little bit further by constructing some of the fields called Stokes fields. So how we construct these fields is, so let us take S1 and S2 and then create a field called S1 plus IS2 you can create. And they are given, S1 is given by this formula, S2 is given by this formula, and if you can see that this can be written as this is called the Stokes amplitude, Stokes 5, S12 field, the Stokes amplitude is this is called the Stokes phase. And you can see that the Stokes phase appears as the difference in the phases in the left circularly and right circularly polarized light in this decomposition, S1, S2. So S1, S2 basically is made up of linearly polarized states. If you take the intensity difference between Ix, Iy, I45, I minus 45, linear states only you have measured the intensities, but it provides an information about the phase difference in the circularly polarized components, RCP, LCP. That is very interesting to note that. Likewise, one can cyclically go and create S23 field that will give rise to phase difference between the Y component. These are orthogonal components basically. Y component of the, if you decompose the polarized light into linear light, X and Y polarized component, the phase difference appearing from the Stokes parameter itself. The intensity measurement itself can give you this also. Likewise, you can also construct S31 Stokes field that will give you minus 45 and plus 45 phase difference linear states. And So Stokes parameters are very much sufficient. Even one can get the amplitude also one can get. Here, as I mentioned here, S12, S23, S31. For a given polarization distribution, in distribution what I mean is, I am going to talk about inhomogeneously polarized light, which means that across the beam cross section, the state of polarization is spatially varying. So in such a case, S1, S2, S3, all these parameters are spatially varying at different locations, different S1, S2, S3 values. So they become distributions, and one can also have the Stokes amplitude as well as Stokes phase distribution. For a given polarization, there are three possible Stokes fields. These are called Stokes fields. Three Stokes fields are possible. And then if you change the polarization, yeah, we have only by intensity measurement, you get the phase information also directly. So in a Jones matrix, you will get X and Y component you take, and the difference between X and Y component, Ex and Ey exponential I delta you write, That delta actually appears here, yeah. So with Stokes in the laboratory, it is easy to do. I'm an experimentalist basically, I'm not a theoretician. So in laboratory, easily measurable quantity, Stokes formalism is always we prefer than the other one, right? If you want to do directly the phase measurement, interferometry or something else, you have to adapt, right? Yeah, Jones matrix, if you want to straight away deal, you have to be careful about that. Here it is with intensity itself, one can deal. All the detectors, photo detectors, intensity only, so it is easier also. You get phase information also embedded in that. Only thing you have to construct the extra field, right? Then going to the next slide. As I mentioned, the 512 gives the phase difference between left and right circularly polarized component of a given polarization state. 23 gives y and x phase difference. 31 gives the phase difference like this. And there are various terms used in topological studies. One is called the absolute phase, which is nothing but the Pancharatnam phase. The other one is called dynamic phase, which is the Stokes phase. We call this as Stokes phase. There are different names in the literature. Stokes phase is actually the phase difference between the orthogonal polarization state, orthogonal eigenstates. This is a dynamic phase. Also, it is a Stokes phase, we call it. And you can see that by taking the Pancharatnam's original paper equation, that is if you take two states on the Poincare sphere, two states represented by point A and B, and if you try to find the interference of these two states, because they are in different states, you have to worry about the angular separation on the sphere also, that is the angular separation between A. No, I'm dealing only fully polarized light. That, yeah, even though I have some publications on that, I'm dealing only fully polarized, all classical, and this itself have large, rich information available, which is unexplored so far, All these things can be extended to partially polarized light also, and also in quantum domain also one can think of. Right, here the angular separation between A and B on the spherical surface, Poincare sphere, is given by C, ABC angles. This is the formula for the resultant one. If you see this is the C is the, if A and B are the same state of polarization, then this term will disappear because C is 0. So it becomes a normal interference equation. And this is the phase difference that is between the two beam which are in the same state of polarization. Otherwise, you have to decompose and then you have to find it. There is a procedure given by Pancharatnam there in his original 1956 paper. And from the point of view of the different phases, the absolute phase is the one that decides. This one, delta, is called the absolute phase, which is also Pancharatnam phase. Actually, it is telling you the wavefront structure. When you interfere two beams, if at all you are getting an interference pattern, bright and dark fringe pattern, that is because of the wavefront structure in optical metrology, you are very familiar. That is the absolute phase, that is delta. And the other one, which whatever is the phase difference here, that is the dynamic phase or Stokes phase, that decides the polarization state. Say for example, a simple example is that if you take X polarized light and Y polarized light, whatever phase difference you give, you cannot create destructive interference. Say for example, if you give pi phase difference between X polarized and Y polarized, that light will still remain as a linearly polarized light, only the azimuth will undergo a change. So the phase difference here between the orthogonal states is along with the amplitude, the component amplitude decides the resultant state of polarization. That phase is the Stokes phase. This is only an introduction about the polarization of light. Maybe in the earlier talk, you would have got much more introduction. Now, this is what I indicated here. This is the Stokes phase. This is C, and this one is delta is the absolute phase, a Pancharatnam phase, we call it. Now, coming back to the polarization itself, instead of using many parameters, we also use two parameters. One is called azimuth, another one is called ellipticity. They can be obtained in terms of the Stokes parameters, S1, S2, by this formula. And one can also, from the Stokes parameters, the amplitudes of the individual components, the X component, Y component, R component, all these things can be, one can obtain this also. And the phases also one can get. The way I'm introducing this is, I'm going to talk about Poincare sphere later and also higher order Poincare sphere later. In all these formalisms, this is very useful. And this is only two angles. One is, we call it the ellipticity angle, the other one is called the azimuth angle. Like in astronomy, people use only two coordinates to position any stars. One from the top, what is the angle, or from the horizontal, what is the angle, only two angles. So that is what here we call it as the gamma and chi, azimuth and zenith angles. And this is in terms of Stokes parameters I have written. In terms of polarization ellipse also, one can define the gamma is the orientation of the major axis of the polarization ellipse. The other one is the ellipticity is the ratio of the major minor axis, right? And one can see that the orientation of the ellipse, you can rotate by without changing the ellipticity also. And also you can change the ellipticity without changing the azimuth also. All these things, how they are represented on a Poincare sphere, we will come back later. And in terms of the major and minor axis, and these are all component, AOAX is component for the amplitude, one can write gamma as well as chi also can be represented in this form. And now this is the background for the polarization. This is the basics what I have talked. So we are going to go slightly deeper inside. To understand all these things, we need to talk about the phase vertex. By now, because it is the third day of the talk, you may be familiar, so it can, so that I can go a little bit faster also. So this phase singularity is an optical vertex where the wavefronts have a helical structure. And what I am going to, here I have given only the phase part, only IM theta part, only the amplitude part I did not bother about that. You will have a donut type amplitude that we are not bothering. And the phase structure is such that if you take an integral like this, del phi dot dl on this, it is turned out to be non-zero here. That is called the topological charge. And now I am going to have a cut here, then cut it and then put it like this. That is called, I call it, any cross section, if the beam is propagating this way, I am cutting it like this and taking that plane and keeping it like this. In topological term, it is called foliation. Foliation of the field. This is the one cross section you will see. This color code here is that the dark is minus pi, white is plus pi. You can go in a right-handed circular path. If you see, it goes like a ramp-like fashion, the phase is varying. So this is also called, the M is called the topological charge. It is also called by winding number. Different names are there for that. And one can have different charges. Also, one can have topological charge plus as well as minus, which means that instead of going the ramp going this way, you can go the other way also. You can have a ramp. And normally this contour integral which I have written here is non-zero for a analytic field. If you see, or if it is a very smooth surface without any singularity, you will see that del phi dot dl over contour integral is zero normally. This actually, if you use the Stokes theorem, it is curl of the gradient times dA it will come. Curl of the gradient, if it is zero, it is a conservative type field where the between any 2 points, if you want to find the phase between phi A and B on a cross section, phi B minus phi A can be written as the integral B A to B, this formula, right? Even the potential also one can find. In electrostatics, you will see the curl of E turns out to be zero. Only when there is a source, curl of E becomes a source, EMF will come inside, right? So you can see that this is actually this integral going non-zero means that this is singularity is there in, enclosed inside the closed line integral. Then one interesting topological feature one can see is normally in any book, Hecht and Zizak, or any famous book in optics, if you see, the wavefronts are separated. This is a plane wavefront notation I have given here. The wavefronts, normally we draw it with a separation of lambda between them. Once I put a vertex on them, this is one first wavefront, second, third, fourth, the wave is propagating this way, let us say. And once I infect the thing with an optical vertex, all the wavefront gets connected by, and it's a single wavefront extending from minus infinity to plus infinity. That itself is a mind-boggling thing. And talking about Huygens principle in construction of the next wavefront from the previous wavefront, all these things become questionable now at this place, because we are completely dealing a different topological structure. And the topological aspects only we are going to talk in this. Many interesting things also we'll see. So to summarize all these things here, in a phase vertex, the helical wavefront structure, the foliation phase structure I have given here, these are called the phase contour lines. Phase contour lines means contour means that any line with the same value of phase values. If you see that along this line you have one phase value, along this line another phase value, all of them are joining there, so there is an ambiguity at the center. So you cannot definitely say what is the phase. That is why the phase is indeterminate at this center here. And the amplitude profile or the intensity square of the amplitude, if you see, it has a donut structure. Now you are very familiar. This is also a profile written here. And the phase structure, instead of using phase contour lines, this is also customary to use real zero and imaginary zero lines. If you write the complex field has a real part and imaginary part, the wave function if you write, real zero you can represent it by this color, red color. The other one is blue color. You can have a, wherever the contour lines cross, that is the position where the vertex is present. Normally contour lines do not cross. In a normal topology, contour lines are not allowed to cross. Only when there is a singularity, contour lines can cross. Contour lines at the maximum can touch each other. They cannot cross. There are certain rules. That also I will talk in this presentation. Now we are only dealing phase singularities. This is putting the foundation for the polarization singularity at a later stage. Now we're looking at the speckle field. Speckle field is in a coherent laser. If you reflect the laser light from a rough surface, you get a specular pattern appearing on the screen, which are dark bright spots here. The intensity variation is here. If you unravel the phase variation, this type of phase structures will be there. This is basically made up of a vertex here. There is another vertex here. This is one is positive, another is negative. They are called vertex dipoles. The large number of vertices will be there. And in a speckle field, the total topological charge is zero. If you start from a beam and then if you get a scattered light, the total, all the topological charge, if you see, the total number is zero. So it is plus minus or equal in number. And in the next one, you can see the phase contour lines. I have taken only 8 phase contours here, 8 different phase values. And phase contour lines, they all meet at this location. This is a vertex location, this is a vertex. You can also see, corresponding to that, you can also see at this place there is a vertex. And whenever the phase contour is having a closed loop, the closed loop is supposed to enclose an extremum, which means a maximum or minimum of the wavefront structure. If it is phase, if you take a simple example of a spherical wavefront, which you get in a Newton's ring experiment, when you do interferometry in a Newton's ring experiment, you see circular fringes, which means that at the center you are going to have an extremum. That is what, whenever there is a closed phase contours, basically interference fringes are phase difference contour lines between the reference and the interfering beam. So you can see that this is an extremum, this is an extremum, and also I have mentioned some points called the saddle points. At this point, they are neither maximum nor minimum, or they are either maximum or minimum. I will show a different picture later. At these points, at the saddle point, the contour line just touch and go. And at that point, we call them as bifurcation line. These are the topological terms commonly used. And this, instead of having 8 contour lines, this is only the real zero and imaginary zero, where you can see the closed, this wherever it is crossing each other, that is the location of the vertices. That is also used to identify where the vertices are located. And this here in one of the papers, what kind of extremum, if there are on a surface, you have an extremum here, it's a hilltop, it is also another extremum. These extremums cannot exist on a surface. Many extremums, if you are supposed to be there should be a presence of saddle point. Without saddle point, you cannot have multiple extremum on a single surface. Saddle point is a basic rule, topological rule, that to have multiple extremum on a surface topology. So in saddle points also, you have different types of rules there, and different names are also there. As I mentioned, this is an extremum here because it is enclosing different height contours. Hilltop, let us see, different heights are drawn here. On a map you could have seen. And this is a point where this comes like this and goes like this phase contours. They don't cross anyway. That is the rule is not violated. Topological rule is not violated. And here also you see here minus plus means this is a lower going down, and this is elevation here. Plus means elevation. These two are elevations, which means that it's a hilltop, this is a hilltop, this side is not it cannot be an extremum here, maximum here, it should be a minimum only. Only these shapes are available. If there is an extremum here, there should be a loop here also. You can have multiple loop saddle points also. Accordingly, they are named. And here what I show is a saddle point which I was trying to explain. The saddle on the back of a horse. If you go from the top to bottom, you go through a minimum. But if you go from the left to right, you go through a maximum. So it's neither maximum nor minimum. Depending on which direction the derivative is taken, the first derivative goes to 0. This is also one of the topological aspects. And in this picture, what I have shown is there is no singularity, only extreme. That is what is in landscape. In maps, you will never have singularities. Only in complex fields we have singularities, right? And this is different names. Open saddle, this is called one loop saddle, closed saddle, and very interesting discussions. The paper itself is so interesting to read. Anybody interested can go through Isaac Freund's paper, which is a very interesting paper. And the next one, these topological rules lead, these features lead to certain kind of rules called sign rules, topological sign rules. That is what we are going to discuss here. This one is called the sign rule, in which in a speckle field, I have shown the zero crossings, red and black crossing. This is a vertex point, this is a vertex, there is a vertex here. Whether the vertex is positively charged or negatively charged, one can easily find. If you know the vertex charge of only one vertex in the whole scene, all the vertex charges can be easily found out. That is the topological rule will tell you. If you have this is a red one is a positive, let us say, then if you are going along the real zero line, or red color I have used for real zero, I forgot by now. If you go along this, it should alternate sign. This is plus means it should be minus when it crossing. Then when it is crossing, it should be plus. Then it should be minus. This is plus, this is minus, this is plus, this is minus, this is plus. So from one, if I know only this, I can tell what is the value here. That is by applying the sign rule, one can get all the vertex charges can be unraveled. And there are also situations like these contours are, there is a vertex here, this vertex is not, this zero crossing is not crossing with any of that. How do you get it? If you start from this end, if you know this one, how do you get it? For that, what you have to do is there are certain rules that you can topologically. What are the axes? Oh, this is a complex plane. It's a XY axis. This is a spatial coordinate. We are talking all spatially varying fields. Spatially in the map, the distances, north, south.
Real and imaginary parts of the spatial field. Right?
Yeah, real and
one color is real and
another is imaginary, zero. Imaginary zero.
Yeah, which is
zero.
Real and imaginary?
Yeah, this is red is real. Let us take. I forgot that. You have to go back to the slide. I want to save time. I have 60 slides, so one of that is zero. Okay, that's fine, right? That's not going to cause any inconsistency, right? So, yeah, what is your question? Which one is what? It doesn't matter.
I'm just trying to understand that you, as you said, that your axes are spatial, right? So
Spatial variation.
What is the length scale over all these things are happening?
Yeah, in a speckle field, you capture the image on a camera, and then you come to the computer and put it on this. The speckle can extend over the whole wall also, on a screen also. It doesn't matter. That in smaller region also speckles can. The size of the speckle metrology decides on what is the geometry you are using. Depending on this, you can have different size speckles also. Grain size is decided by various factors. That's a separate, speckle metrology is a separate unit. Yeah, it doesn't matter here. One can apply all these rules in a smaller level also, size also. right? Everything is spatially varying thing, so it's a spatial coordinate. And the field is complex because the wave function is complex. So one can always extract real and imaginary, and zero you can do. Okay, now this is sign rule I talked. There is also a rule called extended sign rule. By you can tinker with the contours, phase contours. By extending this contour here, earlier it was going like this at the location C. I just tinker it here and then so that it crosses this one. And I deliberately made a cross here. By doing this, I'm not going to have a wrong answer. By doing this, still I will get the same answer if I, okay, here, here you come this way and also you will get this same thing. Come this way also you will get same charge value here if you want. This one is plus, this is also plus. Topological charge. Likewise, by tinkering also you will get the same thing. You see, this is red. I have deliberately created a dark one here. Plus, minus, plus, minus, plus, minus, plus. It will come by doing that. So, wherever the field, this example, I should have taken this one, which is not at all crossing with any of this one, connecting to this, going out of the field. I could have brought it inside and then I arrived at the same thing. This is called extended sign rule. Yes.
As you were saying, that some of the real or imaginary part forming loop and some are open. So what to understand?
No, this one is, observation region is only this much. The whole field, if you take, it is conserved there. Total charge is zero. I am now emphasizing on this slide how the sign rule is applied. And this also, this outside how it is, I am taking only this region of interest and I am just focusing on that. Yeah. Okay. This is called extended sign rule. By creating some borrows or topologically you can manipulate the shape. And this one, these are all foliations basically. As I mentioned, foliation means one cross-sectional field you are seeing. On a foliation only you are seeing it. This one, let us see, this is a real zero contour you are seeing. And a 3-dimension if you see the beam propagation also, this can represent a structure, right? It can be a tube-like structure or it can be like a stone-like structure. This one basically if you do in a 3D. So how to deal all those things? That is actually there only the topology comes into existence. That is what we call manifold. You can have, if you have a regular shape, you can have a name cube or whatever name sphere like that. But you can have arbitrary shape also. So you do the collection of points forming like a clay. You make an arbitrary shape. So a collection of points forming a certain kind of set, such as those of a topologically closed surface, means a clay-like thing you can make an arbitrary shape. That is called a manifold in mathematics. And now what I am going to create is a real zero surface. This is a manifold. I call it a manifold, real zero surface. I created a surface, which is a tube-like structure. And this real zero, and I can always take a cross-section and see on a foliation. This is the observation plane. On an observation plane, when I cut it, the real zero surface appears as a line, which we have seen in the earlier slide. And I have to see this surface, this circle one may represent this type of tube, or it may represent a sphere also. We do not know what, we are not seeing on the 3rd dimension. But what we are seeing only a 2D foliation. That leads to some difficulties, which I will tell in the next slide. And this is an observation, this is the imaginary zero surface if I cross it with the real zero surface. So the crossing of the imaginary zero surface and the real zero surface creates a circle like this. This is actually the vertex trajectory. The trajectory of the vertex means that wherever the zero crossing, if in the 3rd dimension if you go, what is the direction of the vertex core, how it propagates. So what people have found in complex fields, the vertex trajectory can have all kinds of arbitrary shapes, which actually means that if you see the pointing vector around the vertex core, it goes in a helical fashion, the energy propagation. When the vertex core is coming back, the energy is propagating in the backward direction as though even though the beam is propagating in the forward direction. So there are very interesting things like observations like even though the beam is propagating in the forward direction, some local places the energy can light energy can propagate in the backward direction. And some interesting slides also are there at a later stage I will show. And some of the manifolds we are going to consider is called, this is a simple or compact manifold without any hole in that. This is called a torus with a single hole. And this is Tori, that is some authors call it. Actually, it is genus 2 in topology, it's called. This is with 2 handles, this is Tori. And I'm going to deal topology of this and this only in this talk, which means that in our case, we are going to create manifolds which are either compact, or we can have manifolds which are, manifold means real zero surface on 3D space. This type of surface one can create. The beam can be in a random field, one can have this type of structures also. Right? This has a one hole here, this is one hole here. These are all equivalent structures here. And we are going to talk about some interesting things like Mobius strip, which means that you can take a ribbon and then fold it and then joint it on the other side. So if you make an ant to move on this Mobius strip, the ant.
Are they all simply connected domains?
This one is simply connected. Here you will have a hole inside. You cannot on this one, you know.
Inside,
yeah.
Points I take,
yeah, connected. Yeah. So here on this, if you put an ant, it will go on top, and then by the time it completes, it comes to the bottom. That is the interesting thing about, which means that upside is downside anyway, like we call in saddle, maximum is minimum, like that. And also one can have structures like Klein bottle in which the inside is outside. So outside becomes inside. These are all very interesting topological structures. But in polarization singularities, one can create Mobius strips. And using these two manifolds, whether we can create genus 2 like manifolds can be created or not in fields, one can engineer the field. A lot of people have engineered optical fields to have different shapes of manifolds. That also some references I will give, one can go through that. I will give a reference. All of the references are there. Yeah.
So people can realize Mobius strip in the
polarization it is there. Yeah. That is towards the end. I have to go to 60 slides, so I'm worried about that. So I have to go a little bit faster also, assuming that many people talked about singularities. Yeah. Now coming to this is called a Berry paradox, where this vertex trajectory is here. And on a particular foliation, A is a foliation, you will see that 2 dots. One is the vertex is coming out of the page, one is going inside the page. For an observer here on this foliation, we'll see this is a negative charge, positive charge, because the orientation of the phase rotation is like that. If you go through that, you will automatically see that the phase rotation, del phi dot dl, because the singularity is defined by that integral only, for like foliation only it is defined. So B and C, so he will interpret as if there is an attractive force between positive and negative charge, they come and merge and then disappear, they will say. But it is not, actually it depends on the observer how he observes the thing. The reference is given here, you can see. So let us see, you see this case, this can be in a 3 dimension, it can be the imaginary, this is a real zero surface, this is a manifold is real zero manifold, if you extend it on the 3rd dimension. This manifold, let it be like this. If you superimpose on that, on a cross section, this one and this surface, when they cut, the 2 points only will get. So you will interpret it like this. So you do not know what is there, right? So this is naturally called what the interpretation is basically dependent on the observer from which direction, whether it is a positive vertex or negative vertex. That is, it is questionable now. So to deal that, only somehow you have to go to the 3rd dimension and see. Now we can assume that one can create a torus like real zero surfaces, manifolds, in which different types of trajectories are possible, in which this is called the P-type, which can be shrunk into a point, or you can expand the point. It will shrunk to a point. Whereas this is also a P-type. R-type is like on a ring, on a finger on a ring. It cannot be shrunk to a point. Whereas this one is mimicking the surface structure of the thing. And all these things, how they are actually created, this I have taken the manifold as a torus, which is a real zero surface if you take. And you have to take imaginary zero surface and then insert it. Then only they cross, where they cross real zero and imaginary zero is a line. Like 2 planes, when they cross, a line is formed in a cross section. Likewise, this line is a vertex trajectory, means that on the real zero manifold, you are going to insert another structure like this one. It's in the earlier case I have shown. You just insert it here. You will see this. You just insert. That is a cross section. So this itself will give you a lot of idea that what is allowed, what is not allowed. Say for example, if you have this type of structure, which is the trajectory is going this way on the same torus, if you are inserting a surface, if it is a plane, it is fine. If you are using a simple, the first simple compact surface, if you introduce a compact manifold, it has to have a closed surface. So you need to have this R-type, but R-type trajectories can occur only in pairs. It cannot occur in the same way. And their trajectory, one it is going this way means the other one should go in the opposite way. Then only it is. Likewise, here if you are having this type of surface, once you have gone inside, another surface has gone inside, it has to come out. So you should have another pair of trajectory should be there on a torus geometry, right? So you will get pairs which tells you topological rules, like these are the things which I said. This slide is also available on the YouTube as told by the organizers. You can see that. I will come back to this. This on the torus, the two same co-propagating trajectories is not allowed topologically, because if you, this is observation plane, you see both of them have a right circular line interval if you do. So it will have same charge is not allowed. And whereas this is allowed, this one can see from having a torus like manifold, real zero surface. You insert an imaginary zero surface, once it goes in, it has to come out. So automatically opposite oriented one is allowed here. And one cannot have this type of trajectory, linked type of trajectory is not allowed on this type of linked torus geometry. But in a single torus, link is allowed, because anyway these trajectories are not crossing each other. The dotted means it is on the other side, not in the field of view, right? This type of geometry is also possible. These things are very extensively studied by Isaac Freund from Israel and published in Optics Communication. And later, these two are not allowed. And this is what we call a sign rule on the observation plane. The topological outcome of that study outcome automatically gives what are called the sign rules, extended sign rules, all these things. And these trajectories are all actually threads of darkness. And one can, by writing the wave function with the real part and the imaginary part, this is a vertex wave function, let us assume. And the pointing vector is in the direction of phase gradient. A phase gradient in a vertex, maybe in the earlier lectures you would have seen, phase gradient is circulating about a vertex. Vertex itself is a circulatory motion only. The phase gradient is circulating about the core, and the pointing vector has also the z component, so it will go like this along the vertex core. And in Berry Faradas, we have seen a loop like this, which means that the point vector goes and then comes back like this. So which leads to backward propagation of energy in light fields. That also is very interesting feature published earlier. And these are some of the geometries one can design. Engineering the complex fields, one can realize this type of geometries also. Okay, now this is in Nature Physics in 2010. It was 2000 itself, Berry and other people discussed about all these topological aspects. And you can see that this is a torus they have created. This is a torus you can see on that, the possible trajectories there. And this one is the torus is cut open and put in the extended view of that. One can go through this reference. And likewise, this also is, I do not know how to do this. Okay, again another torus, you will look into that. So on a torus, how the links are formed. Link means two loops like that. That is called link, right? That is formation of a link on a torus. This is also in 2021 on paper is there. Now these are all of the phase singularities, and sign rule on lattices also. One can, vertex lattices can be created by various means. Here we have created a large number of vertex lattices of different periodicity and symmetry, and all of them one can see that the topological rule is real zero, imaginary zero is plotted on this. This is a quasi-crystal lattices also can be generated on this. Also the sign rules are properly. These are all charges mentioned here, plus minus, all these charges. The sign rules, non-violation of sign rules have been tested for the topological aspect. Then we will come to the polarization structured light. What? No, it's not 5 minutes. 12:30, 12:40 that I have time. Because we started late 10 minutes, right? Acha, okay. Sorry. Okay, right. So this is a homogeneously polarized light, this is inhomogeneously polarized light. These are called the C points, we call it, or the elliptic polarization singularity. This is a lemon type singularity. I have seen some posters also, Tarak Day students also. So they are familiar with this, so we can go faster. This is what you are seeing is actually a circularly polarized light. This is homogeneously polarized because at any instant of time, vector, the electric field is pointing in a single direction. All the vectors are rotating. Any point you see, it is rotating. The tip is drawing a circle. There is a lag between the rotation here and here, which means that the wavefront structure is different. One is delayed with respect to other on a foliation, right? So these three are homogeneously polarized light with a different amplitude profile, the Gaussian or Leguire Gaussian profile. And inhomogeneously polarized means that this is a vector field I have taken. This is azimuthally polarized. This is azimuthally polarized light. This is radially polarized light. This is with a negative index. So one can also define certain indices. And as I mentioned on a Poincare sphere, one can have latitudes and longitudes. The longitudes are representing the azimuth of the polarization ellipse. Latitudes represent the ellipticity of the polarization ellipse. What I mentioned in the earlier slide, you can see here that if you come along a particular longitude, the orientation, the azimuth is constant, constant azimuth contour, this one, the longitude, whereas this one is constant ellipticity, only the azimuth is varying here. Here the ellipticity is varying, as you can see that. And in polarization singularity, we talk about the azimuth variation. This is a star type variation. This is lemon type, another one is, this is Mone star and lemon. So I am drawing the major axis alone, and while coming along this loop, I am seeing how it is rotating. This is rotating in a particular sense in this way, whereas in the other one it is rotating in the opposite sense, right? So one can assign positive and negative indices, and the del phi is replaced by del gamma here. Phase distribution is replaced by the azimuth distribution. So polarization singularities are azimuth singularities. And one can see the comparison with the phase vertex. The integration, the line integral is done with azimuth here, where it is with respect to phase there. So the mathematical formalism, the index, whatever we have defined, are similar. Here also we have what are called index rules. When you have positive index, here you have to draw the S1 is equal to 0, S2 is equal to 0 crossings. S1 0, S2 crossings, if you go along S1 crossing, the index should alternate in the lattice formation. And this is with the different indices. They all go with the different names: star, lemon, Mone star, then flower, spider web, this type of, this higher index 3/2. So, and here also the sign rule we have talked in phase singularities. Here S1 is equal to 0, S2 is equal to 0, contour lines cross each other. The different colors represent S1, S2, S3, it's all mentioned here. What type of singularities? S2 and S3, when they cross, they also represent singularities, but not in the circular basis. They are in the linear basis singularities. Those singularities are called Stokes singularities. Sign rule, one can see that. And this I will, also one can see the singularities as the superposition of RCP and LCP light, one having a vertex, one not having a vertex. If you superimpose, you will get a lemon, you have got a lemon type singularity here. Here RCP, LCP, the vertex is on the other side. LCP vertex is there, RCP is known vertex. This will also create a lemon. This is a lemons type. This is another type of vertex with a different charge. One can also create same +1 and -1 vertex, phase vertex, but the RCP, LCP, which means that OAM and SAM content, parallel OAM, OAM parallel with SAM, OAM anti-parallel with SAM, one can have with equal magnitude of the topological charge of the phase vertex component field. You will create what is called vector fields, where the fields are linear, azimuthal. These are all very famous fields, quite often studied. And when you tight focus a lemon field, one can create an ellipse field, ellipse distribution in a tight focus spot. When you are using a tight focusing scenario, polarization itself is a two-dimensional phenomena. But the polarization ellipse, when you are tight focusing, that will orient in a third dimension also. So in the third dimension, around the focal region, the ellipse, major axis of the ellipse, if you follow, the major axis of the, because of there is a twist in the foliation, you can see the azimuth twist is there, that will appear as a Mobius strip on the focal plane. So for different index values, the Mobius strip formation, negative index ones, they have focused and they have got Mobius strips. This one is actually experimentally they have realized very recently, 2015, but this idea was floated long time back by Isaac Freund in 2005, even 2005 itself he has floated this idea. And even in 2020 also people try to create, only thing they have to have a very good laboratory facility to have a tight focus. Oh, this one is a ellipse, all major axes you connect. That is the strip. That strip becomes one side to other side. The structure on the 3D space, the orientation of the major axis is like that.
Yeah. Like in the Mobius strips, moving like on a length or
on a length, you know, this is on the focal spot. You are moving around a circle from the center. If you move along that, the major axis of the ellipses, you know, focused ellipses, they undergo a twist like that. One twist, two twists, three twists like that. This is the formation of Mobius strips on the 3D space. Okay, the Pancharatnam phase already I have seen, talked in the earlier slide. I have seen the YouTube Nirmalya Ghosh talk I have seen. One can have this standard Simon Mukunda gadget, quarter wave plate, half wave plate, quarter wave plate with linear to circular, pole to pole transition on the Pankara sphere I am talking. Then so one pole to the coming back this. And if you rotate the center one, you can have different area on that. One can divide by 2, you will get solid angle you find out. And that's called the Pancharatnam phase. This is well familiar by now to all of you. One can have direction also. You can see K vector you can manipulate by using on a coiled fiber if you take, and the K vector can be drawn on a momentum sphere. And then on a coiled fiber, if you can draw the K vector, this solid angle subtended at the center will give you the topological phase. This is also Berry phase, a Berry Pancharatnam phase we call it. And one can realize this for lemons, stars, and all these polarization singularities. Also, one can see the phase variation. So, since there is a polarization, center is a circular polarization. This is if you take a lemon distribution, center is a circular polarization. Around that, values with different ellipticity are seen. So, they actually on a Poincare sphere, this is represented by a region here. This is a lemon at the North Pole. You can also have lemon at the South Pole. Only this each polarization is given by one dot there. So it is giving a region there. So it is difficult to represent here. Whether it is lemon or so, all the states are there. Which way they are arranged spatially, that information is missing here. But this pole to this pole, one can come by simply from RCP to LCP, one can go by using a half-wave plate. One can use a half-wave plate, but while doing that, when you take a lemon from the North Pole and throw it to the South Pole using a half-wave plate, the lemon will become a star, because the index inversion also will happen. That is because of the action of the half-wave plate. One can go through the paper. And by doing this, okay, to explain this, how the symbols have, this is the directrix we call it. All the major axes you can connect. It forms a structure like this. This is a lemon which is a rotated form, which this rotation is related to the Pancharatnam phase, right? Likewise, if you take a star by connecting all the major axes of the ellipse, this structure you can give a symbols further to represent. And by taking a hopping mechanism, a lemon thrown from North Pole to South Pole will come like this. The same half-wave plate which is oriented at a different angle and throw it, it comes to a different orientation. Like that, and then again you go back to the original state to complete the closed trajectory. You start as a lemon, come to star, and then go to lemon. By the way, you come to route 1 and go by route 2, then you will see the lemon has undergone a rotation that is related to the solid angle that is subtended on a Poincare sphere. One can see that. And also, this is actually a circular birefringence. I will go faster here. And one can also see for linearly polarized light, earlier in 2002, Quinn Zan he is very famous. He has shown for tight focusing of light fields how to convert a radially polarized light to azimuthally polarized light. That can be realized by introducing a Pancharathna phase between the RCP LCP component. Yeah, I will write what is come. I will go faster. Right? So one can radial to spiral to azimuthal one can give by introducing the Pancharathna phase shift between rotating one of the half-wave plate, one can tune the polarization variation also. And these are the two books we have published. It's anyway old, 2018, 20 we have published, one can go through that. And to deal this, as we have seen, lemon and stars are represented by a region on the Poincare sphere, but we want to represent as a point on a Poincare sphere. A inhomogeneously polarized light also should be represented as a point. For that, some new spheres are introduced. One is this, I will go faster. I will take this. This is a Poincare sphere here. North pole represents circularly polarized light, plane wave, let us take. South pole represents a circularly polarized light. Only handedness is right and left. So north and south on a normal standard Poincare sphere. And the amplitude, now we introduce a phase variation. This amplitude is constant, phase is constant, so you get like this. But instead, if you have a vertex on the north pole, the wavefront structure is a helix, but the amplitude variation is a LG beam, Legur-Gaussian beam, amplitude donut structure. And here also donut structure with a vertex on the other side, but the charges are different, plus minus here. Opposite charge, RCP, LCP, orthogonal OAM states, any two orthogonal OAM states with differing topological charges orthogonal basically. And RCP, LCP is orthogonal, we know in SAM orthogonal. So superposition of this and this will lead to, because there is a phase variation, the Stokes phase variation, if you combine them, superposition will have a phase difference. Stokes phase will have a variation because this is a right-handed and left-handed helix. So phase difference will be there. That phase difference will lead to polarization difference. That produces inhomogeneously polarized light. So there are a lot of combinations. If you have north pole or south pole with same OAM magnitude, only an opposite in the +1, -1 vertex, RCP, LCP combination and create a sphere, that is called a higher order Poincare sphere. If you take unequal charges, vertex charge, phase vertex, and then RCP, LCP combination and create a sphere, that is called hybrid order Poincare sphere. So on Hobbes, these are many papers that have appeared. That is, you can see that PRL, APL and other things, and hybrid order also has appeared. And as you see in the Hobbes higher order Poincare sphere, one can have these states here, North Pole, South Pole, and by giving a phase difference between North Pole to South Pole, you can go to different latitudes. But here, all the beams are having, if you take any beam, the ellipticity is constant, only the azimuth is having that vertex line integral it satisfies. So the variation of the whole, for a given index, you can have one sphere. For another index, another sphere. That is the drawback here. But every point on the higher order Poincare sphere represents one type of polarization distribution. This is for a Hobbes I have shown, and this is for a this is from our paper. I have taken the figure. You can go to the original paper also. So you can have North Pole, South Pole, and then you can have different locations, different lemons are there. Here lemons I have shown, here also lemons. Only thing, the orientation as we go here, azimuth is, that is actually the Pancharathna phase. On a Hobbes as well as on HYOPS, the latitude, the longitudes actually represent Pancharathna phase, whereas the vertical, the latitudes, longitudes represent Pancharathna phase, the latitudes represent the ellipticity in both the cases. That is the similarity one can have with the Poincare sphere. And for linear states as eigenstates also one can have superposition, and new types of spheres also can be constructed. So this is almost the last slide. Huh? I'm well in time anyway. So, okay. Okay, right. I will finish. I'm very sorry for that. So I did not have a plan. So this one, as you can see, this lemon, I have taken lemon here, and with a different charge I have taken. You can see that the circular polarization is also there. When you come blue to red, this is actually handedness is represented. Linear polarization also there, other side also is. So the occupancy of states on a Poincare sphere is almost full. So such beams are called full Poincare beams, full Poincare beams. These beams are gaining a lot of attention nowadays. Lemon is one example for a full Poincare beam. We also call it a C point. That is the original authors, Dennis and Isaac Freund has given C point and V point. So likewise, one can, I think Nirmal would have talked about this model spheres. You ever talked? Okay, right. Model sphere, you will talk? Oh, sorry. So one can have a LG beam, north pole, LG beam, south pole. Vertex, basically vertex, we can have only, and the combination of LG beams can create HG beams. So one can expand LG beams in terms of Hermite Gaussian beams or Leguer Gaussian beams. Expansion is there, And by giving appropriate weightage to north pole or south pole, the amplitude manipulation or the phase difference manipulation, you can go to different latitudes. Each point represents a kind of beam, which is a combination of LG and HG combination. And this actually, in this one, that is a Pancharatanam phase. That is on model sphere, one can have Pancharatanam phase. This is a normal Poincare sphere. So to summarize, I have less time. Polarization I talked, and I also talked about polarization singularities, topological aspects. Polarization singularities I talked, corresponding sign rules, Mobius strips, some structures, Pancharatanam phase, and different spheres I have introduced. So that's it. Any questions you can ask. Full Poincare beams also. This thanks to research scholars.